Computer. Okay, all right, so let's start the class. All right, so last class we talked about the probabilities, right? So we reviewed the three basic probabilities, right? So marginal probability, joint probability, and conditional probabilities, right? And then today we'll just continue to use these three kinds of probabilities to solve different problems. All right, so the first one, we want to talk about these probability trees. Right, so what is a probability tree? So actually we talked about the decision tree, right? So we say the decision tree, we have a root, right? So we have a root, right? And then we just divide the root into different branches until we have some leaves, right? So we have the root until some leaves. And then we want to make the decision or make the prediction based on the leaves, right? So this is the idea of the trees. So probability tree is also the same idea, but we'll just draw the tree based on the probabilities. All right, so let's take a look at this example. All right, so we say the defects will always occur. So a quality engineer in charge of the production process must monitor the number of defects and take actions if the process seems out of control. Right. So then, in the manufacture of a electronic device, the manufacture problem can occur with the case alignment problem, or the memory problem, or the motherboard problem for an electronic device. All right. So now we have these three probabilities, right? 6% for case alignment, 30% for the memory problem, and 10% for the motherboard problem. Right, so if you want to draw a tree to represent these three probabilities, how would you draw it? We say we want to start with the root, right? So for example, the root will contain what? Will contain all the defects, right? And then these defects can be divided into three types, right? And then we say, let's start with the highest one, right? So let's say the case alignment problem will be 60%, right? And then we have memory problem, which contains, let's say 30% of them will be memory problem. And the other 10% will be the motherboard problem, right? Let's use it for short form. Thank you. All right. Okay, so now we have all of these three problems, and then we want to go further, right, to talk about each kind of probabilities. All right. Okay, so then next here we have kind of a further step. We say what? We say, okay, we have all the defects, right? And I divide all of these defects into three kinds: case, memory, and motherboard. All right, now we say if it is a case alignment problem, we know it is kind of easy problem to solve, right? To fix. Right, and then we say 80% of them can be fixed and 20% of them cannot be fixed. All right, and we have further information about the memory defects. If it is a memory defect, then we say 50% can be fixed, 50% cannot be fixed. All right, and if it is a motherboard problem, then we say it is kind of hard problem to solve or fix, right? So then in this case, we say only 10% of them can be fixed and 90% of them cannot be fixed. All right, so that's all the information we got for now. It's just based on the previous experience, right? Okay, so now let's think about each kind of probability. So when we talk about this 0.60, 0.30, 0.10, then what kind of probability are they? they are marginal or they are joint probability or they are, let's say, conditional probability? What do you think? Anyone? So what are these probabilities? Anyone? Let's say about Julia. Are you there? Okay. Um,
Talking about the ones at the end or the first step of the tree?
the first step of the tree.
Um, would that be conditional?
Conditional, then I'm talking about these three, right? So point
Oh, okay.
0.60, point 0.30, point 0.1, right? So what are they? When we talk about this point 0.60, what's this probability? Actually, we're talking about this is the probability of the case alignment problem, right? Do I care about these defects can be fixed or not fixed when I talk about this point 0.60? Actually, no, right? So actually, we just focus on what kind of defect it is. So we say when we care about only one event, it is a marginal probability, right? And then this is the marginal probability for the case alignment defect. This 30% is the marginal probability for the memory defects, right? And then this 0.1 is the marginal probability for the motherboard problems. All right. Okay. So now let's look at the second step of the tree. When we talk about this, for example, this 0.80, what is this probability?
Is that joint
Is this joint? That
or
means it is a case alignment problem and get fixed. Do you mean that?
yeah. Oh, sorry.
Or let's say, let's compare the two options. What about is I say if it is a case alignment problem, then we have 80% of them can be fixed. Or we say 80% of them are case alignment problem and get fixed. Which one you think it is this point 80?
Can you say it one more time?
Okay, so we say we have two options. It is first choice is this point 80 is if I gave you this is a case alignment problem, then the probability that getting it fixed is 0.80, or this is the probability that it is a case alignment problem and get fixed. Which one you think is more proper way to describe this 0.80?
I want to say like case and fixed. I'm not exactly sure. I missed last class, so
Yeah, no problem. All right, perfect. All right, so then in this case, right, so we say what? We say actually when we talk about this 80%, right, this point 80, right, remember what I said? I said if this is a case alignment problem, then 80% of them can be fixed. So that means I care about both of these two events, but I care about the order too, right? I care about the case alignment problem first. And then based on that, I care about the probability getting them fixed. So then in this case, we say for the joint probability, I do care about two events, but I don't care about the other, right? But if it is a conditional probability, I also care about the two events, but I care about the other. I care about the condition first, and then within that condition, I care about the other event. All right, so then in this case, we say this point 80 is actually a conditional probability. it is not a joint probability yet. Got idea?
That makes sense.
All right, perfect. All right, so then in this case, we say, now, what about this 0.20? How to describe this probability? It is the probability that given it is a case alignment problem, then the probability of not fixed, this case alignment problem not fixed is 0.20, right? And then the other one, this 0.50, this 0.50 is given this defect is a memory defect, then 50% can be fixed, 50% cannot be fixed. The same idea, this 0.10 and 0.9, that means given it is a motherboard problem or defect, then 10% of them can be fixed, 90% of not cannot be fixed. All right, so that means for the second step of the tree, the information we provide here are all the conditional probabilities. Got idea? All right, okay, so now we have marginal probability. We have conditional probability. So we can kind of guess, right? So what is our next step? We want to get a step to get the joint probabilities, right? So actually this probability tree is designed to figure out this kind of problem. All right, so we say, we already know that what is the probability given it is a case alignment problem or defect, then what is the probability that this case alignment problem get fixed? We have already known that, right? It is easy to get that based on our previous experience, which is 0.80, right? But now I want to get the reverse, the opposite direction. I say, I want to know, given a defect is fixed, then what is the probability that this fixed problem is a case alignment problem? Right, so then this probability, we cannot get it so easily based on our experience. All right, so then our goal is to solve this probability. So how to get this probability? Think about it. We can consider this is A, right? This is the event B. So then we have the probability of A given B. All right, is there any formula that we can use to get this probability, this conditional probability? We have what? We have our general multiplication rule, right? So we say our probability of A and B by the general multiplication rule, we have probability of A given B times probability of the condition, which is B, right? So then reversely, that means if I divide the probability of B for the both sides, then we have the probability of A given B equals to probability of A and probability of A and B divided by the probability of B. Now let's just plug into the detail case, right? So that means it will equal to probability of A is the case alignment problem, right? And get fixed, right? A and B divided by probability of B. So B is getting fixed. All right. Okay, so now the whole problem will change to if I want to get the probability of given it is fixed, then the probability that this fixed problem is a case alignment problem can be obtained by this formula. Now from this formula, we need to get what? The top is a joint probability, right? Okay, so then let's think about how to get this probability of case alignment and fixed defects. Think about it. How to get this joint probability? We have still, again, multiplication rule, right? So we still have this general multiplication rule. We say the probability of A and B equals to the conditional probability times the probability of the condition, right? Okay, so what is this 0.60? This is the probability of the case. This 0.80 is the probability of given case that this case alignment problem can be fixed. If you consider this is A, this is B, then you have probability of A given B. And then this is the probability of the condition B, right? So then we have what? We have the probability of A given B. We have the probability of B. So then if we multiply these two probabilities together, is that just a joint probability? All right. Okay, so now let's try it. Right, so then we say if we use 0.60 times this 0.80, right? So this 0.60 times this 0.80. So then we are using probability of A given B times probability of B, which is 0.48. So what is this 0.48? Think about it. What is this 0.48? That's just the probability of A and B, right? So then will be what? Will be, it is a case alignment defect and get fixed, right? Okay, so now continue. What if I use this 0.60 times this 0.2? Now this is the condition, right? So this is the probability of the condition. And then times the probability of not fixed, right? So this is the probability of given it is a case alignment problem, but not fixed. So then we have 0.60 times 0.20. Now we have this 0.12. So what is this 0.12 probability? If we consider this is A given B, and then this is still the probability of B, so then we still get a joint probability, right? So, but now it is a case alignment problem and not fixed. Any questions? Good. All right, now continue. Try it by ourselves. What about the other four? That means now here is the probability of memory problem. And then this is the probability that given it is a memory problem, the probability getting it fixed would be 50%. So now these two probabilities multiply together. So that would be 0.30 times 0.50. Then will be 0.15. right? And then we have probability of it is a memory problem and get it fixed, right? Then the other way, this way, the same thing, 0.30 times this 0.50, and then we have 0.15 again, but now this is the probability that it is a memory problem and not fixed. All right. Okay, so now two more. Motherboard problem. Right, so this is the motherboard problem probability. And then again, this is the probability that given it is a motherboard problem, the probability getting them fixed will be 0.1, right? So then we have 0.1 times this conditional probability. Then we have a joint probability, right? 0.01, which is the probability that it is a motherboard problem and get fixed. Right, the last one would be what? Would be this marginal probability 0.1 times this conditional probability 0.9, which is 0.09. So which is the probability of it is a motherboard problem and not fixed. Got it? Question? All right, so now we kind of got a detailed structure of a probability tree. So we start with a marginal probability, and then based on each case, we have a detailed conditional probability, right? Based on different conditions. All right, and now we multiply the marginal probability with the conditional probability. We have the third step of the joint probabilities. All right, so then the structure of the probability tree is kind of done here. Right, so we start with all the defects. We call this is the root. All right, and then we have different branches until we have the joint probability. We call this is the leaf of the tree. Okay, so now let's look at the leaf of the tree. We say when we had the decision tree, right? So we have all the houses, and then we divide them into different subgroups, right? And then each subgroup will contain quite pure cases, quite pure houses, right? Okay, so now let's think about this case. We start with all the defects. And then we divide them into three subgroups, and each subgroup have two more subgroups. And until we have the joint probability, then we divide the 100% of the defects into six subgroups. Right, so now if you get the sum of these probabilities, you will have 100%, which is 1. That means I have already divided the whole root into six subgroups, which is six leaves. All right, okay, so now again, let's still come back to this question. We say we want to get this probability, and then we had the formula that this probability will equal to the probability of it is a case alignment problem and get fixed. And then divide by the condition, which is probability of getting fixed, right? Based on the multiplication rule. So we say this is, let's consider this is A given B will be the probability of A and B divided by the probability of B, right? Okay, so now let's try to figure out the top and the bottom by ourselves. All right, so what about the top? What is the top? It is a joint probability, right? Okay, so then which one? The case and fixed, right? So then actually it's just a 0.48, right? But now what about the bottom, the condition? I want to get the probability of getting fixed. What is this probability? Are this 0.8 and this 0.5 and this 0.1? Do I want to get a sum of these three fixed probabilities? What do you think?
Yeah, I think so.
So let's test, right? So we say the probability should have a range larger than 0, less than 1, right? So we say the probability must be less than 1. But if you get the sum of these three probabilities, 0.8 plus 0.5 is already 1.3, plus this 0.1 will be 1.4. So 1.4 is actually larger than 1. So that means it is not possible to have this kind of probability, right?
Is it just the case one then? The case fixed percentage?
So that would be this
0.8.
0.80.
Yeah.
Okay, so if it is this one, remember the bottom is we want to find the probability of getting fixed. Okay, this 0.80 is getting fixed, but remember this 0.50 is also a fixed probability. This 0.1 is also a probability for getting fixed. So of course will be these three cases, but remember these three probabilities are all conditional probabilities. Their probabilities are based is within each condition, right? So then in this case, we cannot just look at the conditional probability in this case. We need to look at the corresponding
Oh, it makes sense. Okay.
joint probabilities, right? So they are kind of in the middle things, right? So we want to use the leaves to make the decision or make the prediction or whatever, right? So then in this case, we say this is the probability of getting case alignment and fixed. This is the memory and fixed. This is motherboard and fixed, right? So then what? Then our total fixed probability is that just a 0.48, and then what? 0.15, and then 0.01. Now let's think about the whole problem. We say we want to get this probability, but this probability means given the problem is fixed, then what is the probability that this fixed problem is from a case alignment defect? Okay, so just based on what we had in the last class, we say conditional probability, we need to look at the condition first, right? So we will only focus on the fixed problems. What are they? It'll be this one, and this one, right? Okay, now among all the fixed problems, which one is about the case alignment problem? Is that just the 0.48, right? Okay, so now in this case, you can just calculate this probability, which is 0.75. That means among all the fixed problems, 75% of them are case alignment problem. That means kind of just the most fixed problems are from the case alignment problems. Got idea? All right, so actually the whole probability tree is to solve this very famous theorem in the probability field. We call the Bayes theorem, right? So now if you look at this formula, right, of course, we will not try to use this formula, right? But think about the case, what we did. We say we want to find the probability that given a given fixed problems, right? So they say this B, event B is a fixed problem. Then I want to find AI. So that means one of the cases, right? So one of the defects, which is the case or memory or motherboard defects. So in this case, we look for the case alignment problem. All right. Okay, so then what we need to do, we say the bottom is the summation for all the different cases, just like this, right? So we look for the case alignment and fixed, memory and fixed, motherboard and fixed. But where do these probabilities come from? Actually, we use the conditional probability times the marginal probability. So then you can see the bottom is the conditional probability and marginal probability, so that you have joint probability, and then you get the summation for all the possible cases. And then the top will be just one of them, right? So in this case, we have three cases at the bottom, and then the top will be just one of them. All right, so if you don't draw the probability tree, just like when I was a student, right? I didn't learn about this probability tree before I had this formula, right? It is very, very easy to miss any small situation. For example, in my mind, I only consider these two. I may miss the other one, the other case. So if you just simply use this formula, it will give you a very hard situation, right? So of course, we will not use this formula to solve this kind of probabilities, right? So we'll draw a graph or draw a tree to solve this kind of problems. All right, okay, so this is about the probability tree, but in your essay assignment 10, I want you to look at a more useful application, right? Which is if you're working in the drug field, right? So for example, during the COVID, you have the test kits, right? And then you're more likely to deal with two words, which is sensitivity and specificity. Right. You need to deal with these two words almost every day if you are working on the test case. You want to know how accurate is your test case or something like that. Right. So for example, in the future, right, you work in the medicine company, right? So you need to calculate or do experiments for these two probabilities all the time. All right. Okay, so now let's look at this example. We say ATCs are required to undergo a kind of drug test, right? A simple low-cost urine test is used for initial screening. It has been reported that this particular test has a sensitivity and specificity of 0.96 and 0.93. This means, right? So now we are trying to explain what does sensitivity mean? What does specificity mean? Right. So this means that if there is a drug use, then the test will detect it 96% of time. If there is no drug use, then the test will be negative 93% of time. Right now, based on the previous records or previous results, the FAA report that the probability of drug use at a given time is approximately 0.007. Okay, now try to draw a probability tree for this situation. So here I give you a hint. All right, so setup as start with either they use the drug or they don't use the drug, right? Because here we say this means if there is drug use, then the test will detect 96% of time. So that means what? That means we consider the use the drug as a condition, right? So this is my condition. If there is drug use, then the test will detect it 96% of time. So then how to draw the probability tree at the first step. We start from the root, right? So let's say all the testers, right? So all the person need to have this test. And then what?
Drug use versus no drug
Drug
use.
use, right? So perfect. So drug use, or let's say not use, right? Don't use. Something like that, right? It doesn't matter how you describe it. All right. And then we say here, sorry, not this one, this fine, right? So when we have this kind of probability tree, right, we want to mark our probability, especially for our first step, right? So we want to put our probability on the way to each case, right? Okay, so that means in this case, we want to put what is the probability for using the drug? What is the probability for using the drug?
0.007.
Perfect, right? So 0.007. Then what is the probability don't use the drug? Didn't use the drug.
0.993.
Perfect, right? So because that'll be just the opposite, right? Total is 1. Got it? All right, so then continue. We say these two probabilities are, they are marginal probabilities, right? We only care about they use the drug or they don't use the drug. I don't care about what's their test result, right? So actually we're done with this step. Now next, focusing on their test results. So that means, let's say for this sentence, right? So this means if there is drug use, then the test will detect it 96% of time. So that means if we have the drug use, then what? Detect it. That means what is your test result? Positive, right? So then that means what? 96% of them are positive, detected. Then what is the probability getting negative result? Is that just the 4%? Right? Okay, then the same idea for specificity. That means if there is no drug use, then the test will be negative 93% of time. Right? So actually these two sentences are talking about our popular percentage is called the true positive or false negative, right? So still positive, can be negative, right? Then what is the positive percentage here? If there is no drug use, then the test will be negative 93% of time. So that means 93% will be negative. That means the other way, 70%, 7% will be positive, right? So now these 4 percentage are about, we call the conditional probability, right? And then we need to go one more step to get their corresponding joint probability, right? So how to get the joint probability? We use the marginal times the conditional, right? So that we have the joint. So what we have would be marginal times conditional, right? Next one, marginal times conditional. Next one, marginal times conditional. Marginal times conditional. Right, so then we have, if you calculate for each one, right? So for example, what is this probability? If you calculate this one out, what is this probability? That is the drug use and got a positive result, right? And then this one will be the probability that used the drug but got a negative result, right? And then next one, we didn't use the drug and got a positive result, right? And then the last one will be didn't use the drug and got a negative result. So you kind of divide all the testers' possibilities into 4 subgroups. All right, so now based on this probability tree, can you figure out number A and number B? Number A is asking about what? Number A is asking about what is the probability of a positive result, positive test result. So that means you are looking for a probability of positive test result, right? Do you want to use 96% plus this 70% for both positive results? You say we don't want to do that, right? Because they are all conditional probabilities. So what should we do? So this case is a positive result. This case is also a positive result, right? We want to use the leaf to make our condition or to make our conclusion, right? Then what would that be? This one and plus this one, right? Just like how we calculate the probability of fixed, right? So actually it's just these 3 cases together. And then number B will be finding the probability air traffic control truly use the drugs given that the test is positive. So that means given the test is positive, we are looking for the probability that's really used the drug. So by the formula, how'd you get this probability? You want to use the joint, right? Use the drug and positive, divide by the probability of the condition, right? It's a similar case here. So what do you have? Anyone? I'll give you, let's say, 5 minutes. Try to complete it. Anyone want to check with me? What about number A?
I'm like almost done with it. I just need like more 30 seconds.
Okay, great.
Is it 0.70182?
0.7. No. Try it.
Okay.
So what did you use for number A?
I did the joint probability of both positive results.
Mm-hmm. So is that just a point
Oh,
zero?
that's the wrong. I did the wrong. I
Yeah,
did
I think
less.
you missed a 0 or
Yeah,
something,
I did miss
right?
a zero in this in the second one.
Right.
Yeah.
Right. So it will be just these two cases together. Is that just a
0.07623.
perfect? Everyone? A good? Okay. All right. What about the next one?
I got 0.088.
That's okay. That's good. That just means out of all the positive results, right? 0.07623 out of all the possibility for the positive results, which one is for really use the drug? We say from the tree, we say this is really use the drug. This is no drug, right? So that means this is truly about using the drug. So that would be 0.00672. And then if you calculate that, will be 0.088. Got it? All right. So I will assume you get it. All right. So it's, yeah. I don't. Okay. So now let's continue. Right, so let's continue with the next application of probability. Right, so it is called the market basket analysis. Right, but this analysis is also called the association analysis. It's trying to find out whether two items have any association. So that's, for example, for the grocery stores, you want to put these two items together. Right, so at the beginning of the data mining class, right? So in the video, that guy also talked about this association example, right? So for example, we have the strawberry right? And then we have the cream. And then we want to know whether we want to put these two together in the store, right? Then we want to study about their association. For example, I want to know if people buy strawberry, do they also go and buy cream? What do you think? For me, not quite, right? So I buy strawberry. I may also buy apple, but I will not go and buy cream. But what about the other way? If you buy cream, right? So we tend to kind of add some fruit on the cream, right? So maybe strawberry, right? So then kind of this association kind of has a order, have a direction, right? Different direction has different association. And another example, for example, if we buy computer, right? Do you also tend to buy, let's say, buy a mouse? Maybe, right? Or a keyboard, right? But the other way, if you go and buy a mouse, do you tend to just go buy a computer? Maybe not, right? So then in this case, we want to define a association U that we say it is item set A implies item set B, right? So we have a direction for that. Right, so that means I want to know if people buy the item set A, whether they will also go and buy the item set B. Right, so then to test about the strength of their association, about this association U, we'll use two kind of criterias, right, to test about their association. We call the support and confidence. All right, so now let's look at the first one. What is the support for this U? All right, so if this is U is the item set A implies item set B, then the support just equal to that out of all the transactions, how many transactions contain every item in these two sets? That means if I make it in short, what is this formula? Is that just out of all the transactions, how many transactions contain both A and B? Right? Okay, then what is this one? Think about it. By definition of probability, is that just probability of A and B? Right? We use the joint count divided by the total, overall total, right? So then we have this probability. Actually, this support is just the joint probability, right? So it doesn't matter how you define it. Actually, we just apply the joint probability idea. All right. Okay, so now let's look at this another criteria. All right, what is the confidence? We say the confidence is the transactions that contain every item in A divided by the transactions that contain the items in A. Let's make it in short. What is the bottom? The transactions that contain the items in A. Is that just the number of transactions contain A? Right? And then the top is the number of transactions that contain every item in A and B. So is that just the A and B? Right? If we apply the probability concept here, that actually is just the probability of A and B divided by probability of A. Is that by the multiplication U, is that just the probability of? Given they already bought A, right? Then what? That means given the customer already bought A, then what is the probability this customer will also go and buy B. So that's both A and B are in this customer's basket. Right? So then with this idea, actually what is just a conditional probability, right? Given, right, we have the condition, right? Out of all the transactions that contain A, how many transactions also contain B so that the baskets contain both A and B? All right, okay, so now let's use this simple example to make practice of these two criterias. So here is kind of just a 5 baskets, right? So if you go shopping in the grocery store, you have the baskets, and then for each basket or for each transaction, you have different items, right? Okay, so then we have the first rule. Let's talk about the first rule. We want to talk about the association rule that A implies D. How to calculate the support? We say the support is just a joint probability, right? So it's just A and B divided by all the transactions, right? So then in this case, if we are calculating the support, we want to know how many transactions do we have in here? It will be just a totally 5 transactions, right? And then the top will be how many transactions contain both A and D. How many of them? Let's say this one, right? A and D, this one, right? So how many transactions? Would be 2, right? So then the support is calculated as 2 over 5. All right, okay, so now what about the confidence? The confidence is A and B divided by the total transaction contained A. Try it. So how many transactions contain A? That means I don't care about others. I just count how many transactions contain A. Has already bought A, right? So A, right? So that means there are 3 transactions contain A. Then how many of them also contain B? How many of them contain both A and B? Would be this one. Anything else? Oh, sorry, not A and B. It's A and D, right? So we are talking about this rule, right? We're talking about A implies D. So let's just change our formula a little bit so that you don't get confused. So A and D, right? So then how many of them contain A and D? It'll be this one and this one, right? Contain both of these 2 items. So that will be 2 out of 3. Got it? All right, so I will give you, let's say, 5 minutes to try the other 2. And if you're done, you can continue to think about the last rule. So actually, when we talk about the support and confidence, actually the support is telling you what about their association. Support is telling you that what is the probability that the customers will buy these two items together, right? And what does the confidence tell you? The confidence tell you that if you buy the first item, would you also go and buy the other item? You kind of have a condition, right? So you buy the first item first, and then how much probability you will also go and buy the other item. All right. Okay, so let's look at this C to A. Right, so C to A, so that means the support will tell you how much or what is the probability that the customer will buy both of these two items, right? So then that means out of totally 5 transactions, how many of them contain both of them? That would be this one and this one, right? So that would be 2 out of 5. Right? What about the confidence? Confidence means when you are already out of the transactions that you already bought the first item, which is C. So then this one bought C, this one bought C, this one bought C, this one also bought C, right? So then out of 4 these transactions, how many of them will also go and buy A? This one, right? This one. Anything else? No, right? So that would be 2 out of 4. All right, so similar idea with A to A implies C association. All right, so now let's think about the last association. What about this one? It looks like one side contain not only one item, right? It looks like B and C implies D. Then let's come back to our definition for the association rule, right? We say when we define this association rule, we say it is item set A implies item set B. So that means it may not be just the 2 items, right? May just the 2 sets of items, right? For example, do you want to put the electronics and the fruits together? Right? Then the fruits may include a lot of different kinds of fruits. Electronics also includes a lot of items. Do you want to put these 2 sets together, or do these two sets have strong association? All right. Okay, so then in this case, we say, let me erase that. Then the left side, B and C, we can consider, right? We can consider these 2 together as a set. All right, so that means, let's say, what about the support? What about the support? We say the support will be the probability that the customers will buy both item sets, right? So that means the customers will buy this set and also buy this set. So that means in the basket, it should include B and C and also D, right? By both of these 2 sets. So that means B and C and D out of all the transactions, right? So then how many transactions contain all of these 3? How many? Just the 1, right? So then that will be 1 out of 5. All right, continue. What about the confidence? The confidence means when you already bought B and C, when the customer already bought the first item set, what is the probability this customer will also go and buy D? So then in this case, that means first I need to find how many transactions contain both A, B, and C, right? So that means they have already bought both B and C. This one also bought B and C. This one also bought B and C. So that means totally there are 3 transactions contain both B and C, contain the item set A, something like that, right? And then how many of them will also go and buy D? Which one? Among these 3 transactions, only this basket, right? Only this customer go and buy D, right? So that will be just 1 out of 3. Got it? Question? All right. So now we know the 2 criterias to measure the association, right? But actually there is a problem, especially when we talk about the confidence or actually the same thing for the support. For example, right, when we look at the support formula, we say we care about how many transactions contain both A and B, right? So that means if more transactions contain A and B, then this probability is getting larger, then we kind of assume they have stronger association, right? But what if, let's say, what if A is, what about beef? And B is, let's say, apple. What do you think about their association? We say personally, right, by our common sense, these 2 items should not have strong association, right? But just because, let's say, for example, a lot of people go to grocery stores and just buy apple because the apple is kind of high demand for our daily life, right? It is not because I buy beef and then I would tend to buy apple, or I buy apple and tend to buy beef, right? So actually they don't have this kind of association. It's just because these 2 items are both popular items, then it is quite possible that since these 2 are both popular, then there are a lot of transactions contain both of them. Then if you just use this support to measure their association, you will find this support is very large, right? But it doesn't mean these 2 items have this kind of strong association, right? So then in this case, we say using support and confidence to measure the association is not quite enough, especially for some special cases. All right, so then in this case, we want to introduce another kind of confidence. We call the benchmark confidence. All right, so what is this benchmark confidence? We say when we calculate this confidence or support, right? So let's just use confidence as an example, right? So we say the original confidence is we want to know what is the probability that the customer already bought A, they will also go and buy B, right? So actually we are assuming they have some association. We want to know how large is their association. So that means we are assuming they have some kind of association. All right, and then this benchmark confidence is we want to assume they don't have any association. We assume these 2 item sets are independent of each other. Okay, so now if they are independent of each other, that means A doesn't affect B, B doesn't affect A, right? That means, for example, if I care about B, I don't care about A anymore, right? So then the bottom of the confidence, I don't care about A. That means I just care about all the transactions. The similar idea, the top, since I don't care about A, or just to change to, I just care about how many transactions contain B. So then actually this benchmark confidence is just the B divided by all the transactions. It's just the probability of B. I don't care about A, right? Remember this, what is this confidence? This confidence is a conditional probability. That means with the condition on A, what is the probability of B? Right now, this is the probability of B without the condition, assuming they are independent of each other. All right, okay, so then I want to put these two confidence together, right? So we call this ratio as a lift ratio. All right, so what is this lift ratio? We say the confidence, the original confidence is assuming they are associated. The benchmark confidence, we assume they are independent. All right, now if we take the lift ratio, if we take the ratio of these two kinds of confidence, then think about the case. What if the lift ratio is larger than 1? What about this ratio is larger than 1? Then what does that mean? Does that mean that their association probability is larger than the probability that they are independent, right? So that means if their ratio is larger than 1, that means they are more likely to be associated, right? So then we have a definition. We say if the lift ratio is larger than 1, then we say these two item sets are associated. The other side, right? If the lift ratio is less than 1, if it is less than 1, that means the top is less than the bottom. So that means they are more likely to be independent. Got it? Question? All right, so then in this case, for example, you are the manager, right? And then you calculate the lift ratio, right? You should feel happy to see a large lift ratio or a small lift ratio. For example, if you have a lift ratio, let's say equals to 150, larger than 1, quite large, right? Okay, so you should feel happy about it or you feel not happy about it. If it's large, that means these two item sets are quite associated, right? Their association is quite large, quite strong. That means you better to put these two items together so that the customer's experience can be improved, right? They don't need to buy this item and then walk a long way to another session, right? You want to put these two sessions together, right? So actually, if you go through Amazon's, whatever, just like these kind of large online stores or the grocery stores, right? So actually, they're all using this kind of market basket analysis to decide which session should be close to which session. All right, and Amazon, they are using this market basket analysis to decide, okay, once this person purchase this item, then what other items should be pushed to the customers, right? Something like that. All right, so actually we are done with all the contents, right? Actually for today and also for the whole semester. All right, so now the rest of time, right? Try to figure out questions 3 and question 4. And if you have any questions, let me know. So for this question, I want you to find out support and confidence for this association rule, right? So then this is a item set. This is another item set, right? So you can consider this is A and this is B. So then what is the support and what is the confidence? Try to find the relationship of these three items. That means totally you have 100,000 items, 100,000 transactions, right? And then of these transactions, 2,000 of them contain both orange juice and the OTC, right? Flu medicine, right? And then within these 2,000 transactions, 800 of them also contain soup. So then when you calculate the support, how many of them contain both A and B? That means how many transactions contain orange juice, flu medicine, and soup? How many?
800.
Perfect. So for the support would be 800 out of
100,000.
all the transactions, right? So what is the number of all transactions? Would be totally 100,000, right? Then what about the confidence? The top will be exactly the same, right? So for the support, they are exactly the same top, but the bottom will be out of all the transactions contain A. So that means all the transactions contain orange juice and flu medicine. So be out of
2,000.
perfect. All right, so then number B. I want you to find the lift ratio, right? So we say the lift ratio equals to what? Equals to the original confidence divided by the benchmark confidence, right? So then the original confidence, we have already got that, right? So from the last question, the point is, what is the benchmark confidence? We say the benchmark confidence is just the probability of B, right? And that just a number of observations contains soup divided by all the transactions, right? So how many transactions contain soup? Remember, we have the actual information, right? So once you have the benchmark confidence, you use the confidence divided by the benchmark confidence, you have the lifted ratio. We can also further decide whether they have any association. Right, so I'll leave this question to you. And if you are working on question 4, it is just to kind of give you the information in another format, right? In a two-way table format. The
What did
CV.
you, oh,
Yeah,
sorry.
sure.
What did you get for 3B, the lift ratio? Was that point? I got 40.
Yeah, that's correct.
Okay.
You're on the right track.
Awesome. Thank you.
So question 4 is a little bit challenging, right? Think about it carefully. So first, let's think about how to calculate the support. Support is the probability that contain both of these two, right? That'll be saving and checking divided by all, right? By the definition, right? So this is A implies B. Okay, the point is how many of them? How many customers contain both saving account and checking account?
5,000.
Mm-hmm. Now I think you got the idea. And what about the confidence? That means out of the customers that, no, not all, contain, out of all the customers contain A, right? So which is customers having saving account. Out of these customers, how many of them also contain or also have checking account, right? So that's they have both of them. So how many of them? The top is the same, right? 5,000. The top is the same, but what about the bottom?
Is it 6,000?
Mm-hmm. Perfect. I don't care about they have the checking account or no, right? I just care about how many customers have saving account. So that would be all of them, right? So the total of 6,000. Now the benchmark confidence. Again, this is A, this is B, but benchmark confidence is the probability of B, right? So actually you just care about how many checking accounts out of all the transactions. So how many checking account do you have?
$8,500.
Perfect, good. Right, so I don't care about they have the saving or not. I just care about the total for, yes, of the checking account, right? So that would be 8502. Then for the last two questions should be quite easy, right? So you just use the confidence divided by the benchmark confidence.